Well, good afternoon, everyone, and welcome to this second presentation in our short series on AC interference. For those of you who don't know me, because I might look like an unfamiliar face, I'm not Vanessa Seeley-Fisher. Vanessa is unfortunately indisposed, and so I have the honor to host our session today. Last week, we spoke about the corrosion aspects of AC interference. And this week, we're going to look at a slightly different angle, and that is of electrical safety that is associated with AC interference on pipelines resulting from their proximity to power lines. And to discuss this, I'm going to welcome a special guest. Daniel Hovy is a pipeline engineer who's been in the industry for quite a few years and specializes in the AC interference that occurs between power lines and pipelines. So Daniel, welcome, and over to you.
Good afternoon, Neil, and everybody listening in. Thank you for the opportunity to be a guest here on the bite-sized corrosion. Daniel,
please elucidate for us what is actually meant by electrical coupling between pipelines and power lines. That is I believe, the technical term that is used.
Electrical coupling between power line and pipeline becomes an issue when the effects are more than just a nuisance. And sufficient coupling depends mostly on the length of parallelism between the pipe and the power line, the distance between them, and also the current load or the ampere load on the pipeline. And these are the main issues. Then the question is, can we avoid and how can we avoid this? And yes, we can by putting the power line and pipeline as far away as possible from one another. And then we ask, how far is far? Joburg and Cape Town is far enough. But then a few kilometers is often not far enough. A rough guideline on the distance the investigation needs to focus on, we can determine with the zone of influence study. I'd just like to refresh our memories with the three types of couplings that can occur, the inductive, the conductive, and the capacitive coupling. And I would just like to share my screen to illustrate these mechanisms. The first mechanism that we're looking at is inductance. And here we have a power line and the tower or the pylon with the power line, the current carrying conductor. And we know from the current in the conductor, we have an electromagnetic field that's generated around the conductor. Two things we need to note of this electromagnetic field is the one, it's at right angles, 90 degrees to the conductor. And number two is that this field is not a static field. It varies due to the alternating current. We have got the electromagnetic field varying in tandem with the current from zero current to maximum current to zero to the other direction. We've got the electromagnetic field also building up to maximum, collapsing to zero and to the other direction. This electromagnetic field then cuts through our pipeline. Should this pipeline be a bare pipe, it's no matter, no cause of concern, because the current that is induced on the pipeline can just climb off the pipeline, go into the earth, and then return to the source. In our case nowadays, we are coating the pipelines and we're making a very good job of this coating. We are providing coatings with excellent properties, with very few pinholes, very little chance of electricity coming off the pipe. So in this case, the electricity current that's induced on the pipeline cannot come off the pipe. And if I can use the analogy of a balloon, if I blow air or current into the balloon, the air cannot go anywhere. It's in the balloon, and the balloon just gets expanded, and the pressure in the balloon is then the same as the voltage that then increases in the pipeline. The second mechanism is the conductance, and this is where we have a fault from the current carrying conductor fault onto my tower or onto my sky wire, my ground wire. So we've got a fault to earth. And this fault then is a short circuit current flowing through the pylon into the earth, and it wants to return to the source, which is the substation. In this case, the current in the earth sees this superhighway. There's a pipeline there, which is a low resistance metal, and the current climbs onto the pipeline and it passes along the pipeline back to its source. Should we be standing somewhere here, we're standing on zero earth potential, say remote earth, and the pipeline is at some crazy high potential. We touch the pipeline, our feet is on earth, and due to the potential difference, we are going to be part of the electrical circuit and we are going to get a shock. The third mechanism is capacitance, and this is where we have the pipeline stored next door to the trench, and typically we put the pipelines on skids or wooden poles, and these effectively can isolate the pipe from the ground. In this instance, we've got a capacitor and two capacitors in series. The first plate of the capacitor would be the conductor on top, and the second plate is the pipeline with the air dielectric in between. So this is the first capacitor, and the second capacitor in series is a pipe again, and then the earth at the bottom with the dielectric in between. And this capacitance, the voltage generated on the pipe, is very much dependent on the voltage, not as the inductive case where the inductive is dependent on the current. This is dependent on the voltage and then also on the distance and the air permittivity, of course. From this, an electrical shock can be experienced, and also a spark can cause fuel ignition.
Yeah, so Daniel, in that situation, obviously then working close to one of these new 400 kV power lines or 765 kV power lines is a lot more dangerous than, say, the lower voltages. I do remember a situation recently where we had a contractor who downed tools during a pipeline construction project because they were getting shocks from the pipe next to the trench.
Yes, this would typically be a capacitance issue, and the pipes would have been isolated sufficiently from the ground on skids, and the potential is generated on the pipe to be part of the capacitor as the part of the electrical circuit. Then something to note, although the potential can be thousands of volts, the system has very, very little energy, so it just got a cause of shock sensation. The shock would not be fatal, but the associated actions of the shock. And there, typically, our bodies are built this way. If there's a shock, we withdraw, and we withdraw to such an extent through the fright. We step back, we step into the trench, we step back, we step off the ladder, or we step back into traffic. So the associated actions is actually where the problem lies. And that is why it's important to mitigate. And then the question often asked, okay, when is it necessary to mitigate? When is the problem likely to appear? And it's difficult to calculate this, but generally the guidelines tell us when a pipeline is closer than a kilometer, then we should start monitoring the situation. And then how to mitigate. Fortunately, Neil, is very easy to mitigate. We just earth the pipeline by putting a steel or even a copper or a steel peg into the soil, and we just we ground the pipe with just a small wire that we connect to the pipe, and then the system is grounded and we haven't got the problem.
Yeah, so that's a bit like stroking a cat on steroids. So that happens when the pipe's above ground. So then presumably when we bury the pipe, the problems go away.
And now our real problems start, and these problems are there and they remain there. And then we have two types of issues that we look at. We look at this touched potential and the step potential. And then we've got two conditions, the steady state and the faulted power line condition. And I'd just like to define these four terms so that when we carry on that everybody's comfortable in understanding what we mean with that. Steady state is when the power line is stable with the current load that changes as the requirement change. The change is not much. It's as the town or the power supply it's providing for changes. Typically in the night, you've got a lower demand of current, and in the daytime, you have a higher demand. As we'll see in future slides is that we have got a varying, but it's a stable. The other thing that we need to evaluate is the maximum potential load on that line, and so it's line specific. Each line would have its specific maximum potential load. The faulted condition is usually phase to ground, and this we regard as a short, and it's a short duration event which lasts as long as the circuit breaker, which is automatic. If there's a short, the substation can see the short and the breaker would automatically disconnect. Typically 0.5 of a second down to 0.1 of a second, but often we use 2.5 of a second. Typical faults of fault to earth happens on the power lines due to bird streamers, fire, pylons breaking, and I've even seen photos where the guys have started stripping pylons, taking out the cross bracing, and that pylon is just standing there. The next sharp wind that comes will just the collapse, and then we've got short circuit conditions. The next slide shows a few examples of touch and step potentials. Touch potentials, if it's from hand to foot or hand to hand, and then the step potential is typically a step of 1 meters where we've got a potential gradient between that foot and the next foot, sufficient potential gradient, sufficient enough to create a current flowing through the body. Obviously, the current flowing through the area where the heart is creates more problem than just going through from foot to foot.
So Daniel, these shocks that we get, at what level do they actually become a hazard to life and limb?
Neil, the safety issues are unfortunately real, and it's something that the pipeline owners or we have to take cognizance of, and it's something that can get nasty, and there can be a fatality from such a shock. The guidelines are based on the IEC guidelines and rules and regulations, and it's much the same world over. We really are using the same standards as the world is using. For steady state, the origin of the safety limit is from a body current of 10 milliamp, which is the maximum let-go current for men. And this is reduced to 5 milliamp, where pipeline is exposed to general public and especially for children. A handy voltage limitation is derived from this 10 milliamps by using Ohm's law, where voltage is current and resistance. The body is the resistance, the current is the 10 milliamp, and then we get to our touch potential at steady state of 15 volt AC with a 7.5 volt AC for general public. At the faulted condition, the criteria differs because it's a short duration and the body can withstand a much higher current for the shorter duration. And typically we're looking at touch potentials at faulted conditions between 60 and 300 volt. And this is the difference is due to the duration, the resistive layer that we put down, either a stone or an asphalt layer, and also between the public, which has got a lower threshold, than the staff, which is a higher threshold, as we assume that staff would have the necessary protective clothing. Step potential at faulted conditions is typically between 70 and 800 volt.
What sort of voltages can we then expect to see on a pipeline? If we've got a new pipeline that's been put in the ground and nobody's taken any measures to mitigate the faults or the inductance, what sort of values have we actually recorded on pipelines?
Neil, the values that we have, I've got some examples here. I haven't experienced it myself because I wear the safety boots and I don't go prodding around looking for trouble. Verbal confirmation I have received from guys working in the pipes, from a tickling sensation to I really feel bad, I don't want to go and work anymore. The pipe has shocked me. The slide showing now is potentials taken at a pipeline, just a spot reading, and there on this 12-kilometer pipeline reading at steady state condition was at 4.5 volts and 2 volts and 1 volt. So this just shows the changing voltage on the pipeline in the position, and it depends on the pipeline relative to the power line locality.
Those are not considered dangerous, obviously, from a shock hazard point of view.
No, those are not, but the next slide is from a data record. So at that stage, we might have just taken it when it's at a low state. So what we do, we install data loggers, and this data logger at the pipeline was installed at about 4 o'clock afternoon, and it ran for 12 hours to 5 o'clock the next morning. And on the left-hand axis, we see the AC potential. It started off at a 10-volt potential, and then it went up through 16, and it hovered around between 16 and 18 volts. It hovered around for 2 hours, and then it went down, typically with a load that went down in the middle of the night. We've got a low load. So there's a real situation where at a steady state, you could have had a problem. When we do modeling, the modeling also gives us this indication. I've just showed two conditions here, the steady state on the right-hand side. This is a pipe of 12 kilometers, and our threshold is the green line at the bottom of 7.5 volt at steady state. And in this case, the model shows us that we're running at 100 volts, coming down to about 20, and then coming up and down again. And then on the left-hand side, the faulted condition, we're looking at 60 volt touch potential, which is down here. And if we fault this power line, II2 power line, then we have got this happening on our 12-kilometer pipeline from 600 volt coming down. If we fault our power line AH3, then we've got a different signature on the pipeline, and we have got this one coming up to 1,400. So these are real figures, and it's issues that we need to mitigate.
I certainly remember measuring a voltage of something close to 500 volts short term when we were doing some interference testing on one of the power lines. Daniel, given that these voltages occur, which are obviously way in excess of the allowable thresholds, and we saw from your previous graph that the steady state may not, in fact, be there all the time, but there are certain times of the day. But it's long enough that somebody touching the pipe under that situation is effectively subjected to a continuous voltage at that level. What can we do to protect the people is the one question. And the other question is, what can we do to reduce these voltages? If you can't reduce the voltages, how do you protect the people, and vice versa?
The first step is to analyze the electrical system, and it's quite a complex issue to do due to the number of variable inputs that we have. The calculations are complex, and we use computer programs to do this. The vast amount of variable inputs take time to obtain. And for instance, we need to determine the power line system. We need to obtain steady state load values, power line fault values. These we get from the power line operator. From the pipeline operator, we get information of the pipeline. We need to understand the deep soil resistivity, the soil resistivity of the area, and also the geometry of the pipeline. And these are to name a few. The first prize, of course, to mitigate is by removing or reducing any of all the issues. But we often cannot because we are not in control of all the issues and aspects. And I'd like to just show some typical modeling views of the model. This is a right-of-way modeling. This system is like an AutoCAD format where the pipeline is somewhere in there, and all these others are the power lines. And this is then modeled. This is a very complex system, and this is then modeled on the program. The web-like structure, the spider structure here, are the small regions that the program creates for itself, and each region is then calculated. And these regions then, the program uses this and builds a circuit. And the circuit looks something like this. That each phase is like phase. This will be power line, pipe, etc. And these things are connected by means of connections. We do certain mitigation. We test the mitigation according to such programs. This is one typical program. There are many programs that can do the work. This is one of the programs that is used in the industry. The mitigation measures, it's not that complex. It's more complex just to do something practical. One of the mitigation measures is that we have got the pipeline installed here. It's a coated pipeline next to the power line. And in this case, we've got an induced current, which we need to bleed off, and we do it by grounding the pipe. So you install two metal conductors here, and this looks like a zinc ribbon, continuous zinc ribbon, both ends, and we connect the zinc ribbon to the pipe at certain localities. So the current that comes on the pipe has got a path to climb off the pipe into the earth and return to its source. The mitigation is twofold. The one is that we are reducing the voltage on the pipeline by grounding the pipe. The second part is that we have got a ground potential rise, where the ground potential also rises due to the current coming off into this bare conductor. So the two aspects then assist to mitigate the issue, to make the place safe. The second way is an equipotential plane, and in this is where we create either a grid, which is better than this example here, which is just a straight line conductor laid down. But essentially, we create a grid or a plane, which we then connect to the pipe. And in the example here, we've got a test post. The test post is connected by means of a cable through to the test post, and we can access the test post. Should we be standing at the test post, we touch the test post, thereby we are touching the pipe. And we are standing on this equipotential plane. There's a fault, the pipe is at 0 volt. There's a fault, the pipe goes up to 10,000 volt and then goes down to thousands of volts, comes down to 0 volt again. we don't feel anything because we are standing on the same potential. There's no potential difference between us and the pipe itself. And therefore, we don't even know that anything's happened. We won't even know there's this tremendous event that has taken place.
That's a bit like the birds perching on a high voltage wire. They don't get electrocuted because they're at the same potential as the wire.
Then, Neil, just to show the mitigation, one of the models that I can just explain by way of a model that we've done at faulted condition. This is before we did any mitigation. This is an 8-kilometer pipeline. We are showing three pipes here on the graph. On the left hand, we've got the touch voltage, and we have got the 8-kilometer pipeline. The red line there is our 60-volt touch potential criterion, and we can see we're okay for the first kilometer and a half, but thereafter we are exceeding, we're coming into 300 volts, 250, 300 volts. So we need to mitigate this. We do our tricks, we do our fancy stuff, we do our grounding. After mitigation, we come to this situation where we've got the same 60 volt there, everything is calmed down, and we're okay, we are safe. The spikes here are typically where the conductive element comes through, where we've got a tower or a pylon very close to the pipeline. This one here, which is exceeding the safety, might be a tower which is very, very close to a pipeline, and we can mitigate that by putting a nodal grounding at that point if we need to. The difference between the two graphs is here we are putting the fault current on power line II21, and this one we are putting the short on power line IZ1.
So it's obviously very important to analyze all the power lines that affect the situation. But Daniel, before you go into this last summary, just one thing that jumps out at me, you've been talking about grounding the pipe to remove the AC, which is great from an AC safety point of view. But now I'm going to put my cathodic protection hat on and say, oops, from a cathodic protection point of view, we want to have the pipeline well insulated in order to minimize the current requirement. And here you go along and connect the pipe back to earth. How on earth do we couple these two contradicting requirements?
Well, the one way we can do is to say, well, I don't care, and I go off, I've done my thing. But we're not that nasty, and we do know that CP impresses current on the pipe, which is coated, and the excellent coating, the result of the excellent coating is that we've got such a low current demand from the CP. Now, when we ground correctly, so we ground the pipe with a bare conductor, so we're increasing the bare part of the pipe, and the CP has to put on a lot more current to still maintain that negative potential need for the pipe. And the CP system would not be able to do this. So in this case, we decouple our grounding system from the pipe, and we install a decoupler between the two. And this decoupler will then DC decouple. So the CP system doesn't see this bare metal lying in the ground. It's DC decoupled, but it retains AC coupling. And it's much the same principle as a battery with the plates.
It's like a capacitor which conducts AC and blocks DC.
Yes, Neil. This is one manner which a person can show all the issues that we need to mitigate, red being we need to mitigate and green not. But the issue of the slide is that the issues that we are looking at is the safety and AC corrosion from a steady state perspective, and then the fault, which we are looking at safety. And the mechanism that we do to mitigate, we see here is grounding by zinc ribbon wire, grounding by zinc ribbon wire, grounding zinc ribbon wire, and their equipotential plane. So the combination, the mitigation, the same mitigation does a number of things that it does and addresses. So it's one system which collectively looks after a number of issues.
Daniel, so thanks so much for giving us a very comprehensive overview of the situation. This is obviously a lot more complex that one can cover in 30 minutes, but I think you've done a great job in highlighting the issues that we face from an electrical safety point of view. Next week, we're going to wrap up this little discussion series on AC interference, and we're going to be welcoming Arthur Berger from Eskom, who is from their high voltage division, and particularly power lines, obviously. And he is going to elucidate for us some of the steps that Eskom have taken with regard to ensuring that people are safe when they're working around pipelines. And to this end, Eskom has put in place a guideline for powerline pipeline interaction and the measures that can be taken. And we'll be unpacking that next week. Thank you and goodbye.